Hey guys, welcome back. Today we're going to be focusing in on tree diagrams. We've already looked at it a little bit before, but we're just going to do it standalone today. We're also going to answer the question, do larger families travel less? So at the beginning of the year, I had you guys take a survey, and two of the questions in the survey that I asked are how many siblings you have and how many states that you have visited. So we're going to see if having larger families tends to travel more or tends to travel less. We'll see. All right, so broke it down where we had 45% of my students had 3 or more siblings. We'll consider those, I suppose, a larger family. And then 75% had traveled to 5 or more states, and 38% had done both. So if we subtract those two, we can find the disjoint probability of having 3 or more siblings but not having traveled to 5 or more states. And then this is the overlap. 37% would be those that have traveled to 5 or more states that were not a part of a large family. And then 3 or less siblings would be 55%. Notice that's just the complement of the 45%. And then 18% are those that were a part of a small family that had not traveled to 5 or more states. So we have 3 different marginal distributions here and then 4 disjoint ones. Okay, so on this one, we want to find the probability that you had traveled to 5 or more states given that you had 3 or more siblings. So of those who had 3 or more siblings, that's out of the 45%. So that's going to be in the denominator. We're looking for the 38%. So 38 out of the 45% would be 81%. And then the conditional probability of traveling to 5 or more states given that you were part of a smaller family. So out of the smaller family is 55%. And then having traveled to 5 or more states would be this 37. So 37 out of 55% would be 59.6%. So just looking at the 2 conditional probabilities, it looks like if you were part of a larger family, you were actually more likely to travel to do a lot of interstate travel or travel to 5 or more states, just from my students, but kind of interesting. All right, so another way, and the best way that we'd actually test for independence and what they want to see on the AP test is we want to compare the marginal to a conditional probability. Well, if we have a marginal distribution or a marginal probability of 70% of all my students have traveled to 5 or more states, we want to compare that to one of the conditionals, whether it's the conditional for having more, 3 or more siblings, or for the smaller families of 3 or less than 3 siblings. And that would be 81%, and 81% is not the same as the marginal, so it looks like being a part of a larger family increased your likelihood of traveling to more states, so they would not be independent. So independence and disjoint are actually 2 completely different things. 2 things are mutually exclusive or disjoint if it's not possible for them to have any overlap, so if their intersection is empty. So for instance, whether or not you had 3 or more siblings, that and having less than 3 siblings, you can't have both of those. So there's no overlap between the 2, and you notice that they add up to 1 between the 2 as well, which is kind of cool. But having 3 more siblings and traveling to 5 more states, those are 2 events that do have an overlap. And 48% had 3 or more siblings, and 70% had 5 or more states. And then these 2 would actually be independent if we took 70% of 48 or 48% of 70%, and that would give you what the expected overlap would be for those 2. I think for us it was 38%, where we would have expected 34%. So the area in between them was a little bit larger or a little bit more overlap than we would have expected if they were independent, meaning that having a larger family meant you were more likely to do more interstate travel. So our general multiplication rule allows us to have 2 events that are not independent. So when they were independent, we could just multiply them together to find out what the overlap would be. But if they're not independent, we have to use a conditional probability. So the probability of event A and B occurring is the probability of A times the probability of B, given that A has already happened. So this is conditional probability is best modeled with tree diagrams. So the first event is going to be the first branch, which is going to split from our 100% to whether or not you're part of a big family, which was 48 and 52%. So that's our first event, the probability of A. Then knowing whether or not you were on which branch, so given that A has already happened, what's the probability of event B occurring? And these are all going to be conditional probabilities given which branch you were already on. So the conditional probability of having traveled to 5 or more states, would be 39 out of the 48%, which is 81%. If that's 81%, then we have 19% that haven't, because those 2, of course, have to add up to 1. And then out of the 52% that were part of smaller families, 31% had been in 5 or more states, so 31 out of 52 is 60%, and then 40%, of course, would have not have been. to 5 or more states. All right, then define the actual intersections, which are going to be the disjoint probabilities, which are all 4 of these. So either here, 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 or here. That would multiply it by the first event times the conditional probability for the second one, which would give us these probabilities here, so that times that. Also, if this has to add up to 48% of the total from our first branch, then these two have to add up to 48%. So you could do 48 minus the 39, which would give you a difference of 9%. Same thing, 60% of 52% is 31, and if that has to add up to 31, this one has to be 21. Kind of cool. And then all these probabilities together, all 4 of the disjoint ones, have to add up to 1. So the probability of only having 3 or more siblings but not having traveled to 5 or more states would be 9%. Probability of both would be 3 or more siblings and having traveled to more, which would be 39%. So 5 or more states but less than 3 siblings would be 31%. And then 21 is the only one left over, so it has to go there. So it's kind of nice to model these out here, but we also have the marginal distributions, which are here. Kind of blown out there. All right, so if we wanted to reverse the condition, so if we have the probability of A given B and we want to find the probability of B given A, so we just want to switch the conditions, it's not that simple. There is something called Bayes' rule, and apparently Reverend Thomas Bayes looks a lot like Charlie Sheen. I thought that was kind of interesting. So if we wanted to reverse those conditions, we could actually use this formula. It's kind of a disgusting, nasty formula, but just wanted to show it to you. It's there. All right, so let's look at some of the set theory stuff. This won't take us very long. So the union is A or B. Remember the or guys that would have whether A or B or both. But myself, I'm an and guy, and that's why I'm still single, and other reasons probably. But anyway, and is the intersection of the two. So it's the upside down U. Then we have all of our ors are going to be implied to be inclusive, but sometimes we have exclusive ors. Like for instance, are you going to put the summer tires or the winter tires on, or the all-season tires? You can't put all of them on, so you have to choose one or the other, but not both. That would be an example of an implied exclusive or, but they won't be implied for us. They'll tell you that you want A or B, but not both. The set A is defined as A toss B, A minus B, which is just the portion of A, like the disjoint one. But then we add the intersection of A and B, which would give us this part here. So that's all the things that are event A. The complement of A is going to be the sample space, which is the whole thing minus A, everything that's in A, which would be S minus A, or the sample space toss A, which would be its complement, which is just 1 minus the probability of event A occurring, by the way. Here, you don't really need this, but it's kind of cool what we're doing in set theory. B is a proper subset of A, and so we'd say that it's a proper subset where it's strictly less than, but it's a U because we're talking about sets. If we had a line underneath it, then it would just be a subset, which might be an improper one where they're actually the same set. Then A and B are disjoint, meaning they're mutually exclusive. All right, so let's do 3 examples, and then we're done. All right, the question is, do you smoke was asked of a random sample of 100 people. The results are shown below. So the first thing we want to do is actually find the marginal distributions here. So what's the total? And we're dealing in counts instead of percentages, but because it's 100 people altogether, it'll be pretty easy to find the percentages. You just move the decimal place. So adding these together, we get 31 smokers, which means we have 69 non-smokers. Adding those together, I think we have 60 males, and then of course 40 females because it had to add up to 100. So what's the probability that they smoked? So the overall for smoking would be 31 out of 100, which is 31%. What's the probability they smoke given that they're male? So of the males, now we're only interested in 60. Of those that smoked, that would be 19. So 19 out of 60, which is 31.7%. Now, I don't think it's even possible to get these two numbers any closer, the marginal to the conditional. So at least based on this sample, it does not look like there's really any evidence of an association between smoking and sex. So it looks like the males and the females are equally as likely to smoke. So is smoking independent of gender? We would have to say yes. The probability that one smokes is 31%, which is approximately equal to the same as those that smoke given male, which is our conditional probability. You could do the same thing with the female. It would be slightly less than the 31% because the 31% would be the average, the weighted average actually. A company manufacturing electronic components for home entertainment systems buys electrical connectors from 3 suppliers. The company prefers to use supplier A because only 1% of those connectors are proved to be defective, but supplier A can only deliver 70% of the connectors needed. So we're going to have three different suppliers. Supplier A, they just said, was 70% of all the connectors they buy with a defective rate of 1%, meaning 99% rate of, or 99% of them are not defective. Then for supplier B, 20% come from supplier B with a defective rate, and the rest come from supplier. Okay, so that would be 90%. So 10% come from supplier C. The defective rates from B and C are 2 and 4 respectively, means it's in the same order as what it was said before. So B would have the 2% and C would have the 4%. So 2 and 4%, which would mean there was 98% okay and 96% of them are okay. Okay, fill in the tree diagram. So we've got our first event, which is which supplier it came from, A, B, or C. That's the first branch on the tree. And then the conditional probability would be the defective rates given each respective one, right? And then to find the overall disjoint probabilities of whether or not they were defective and from A, we would just simply multiply them together. So that would be 0.007. Then the remaining ones have to add up to 70%, right? So that would be 0.693. And then 20% of 2% would be 0.004. And that has to add up to that. So it would be 0.016. Or 196, whatever, you get the idea. Same thing, that would be 0.004, believe. Again, same rate as that one, kind of cool. Same overall total as that one. And then adding those together, they have to add up to 1%, so that would be 0.016, or 0.096, sorry. Okay, so got those. Now that we have those, we can answer the questions. What's the probability that it came from A, given that it was defective? So we have to find out first, what is the overall marginal distribution or marginal rate for defective? So add all the defective totals together. So whether it came from A, B, or C. So that's going to be 0.7% plus 0.8 plus 0.4 plus 0.4, which would be 0.15%. And then that it came from A would be A and defective, which was 0.07 or 0.007. And that's a total percentage of 46%. I believe something's going on wrong there. Yeah, 46%. Repeating. All right, what's the probability it was defective given that it came from A? Well, that conditional probability is actually already here. So if it came from A, the defective rate was only 1%. So we've already got that one. All the conditional probabilities are pretty easily shown whenever using a tree diagram, at least going one direction. If you did it the other direction, you have to do it like we just did. All right, suppose that 23% of adults smoke cigarettes. It's known that 57% of smokers and 13% of non-smokers develop a certain lung condition by the age of 60. All right, so it said 23% smoke. That means that there's 77% that don't, that they develop a condition, 57% of smokers and 13% of non. So that you didn't develop the condition would be 43% of smokers and 87% of non-smokers. And then we just multiply the first event times the conditional second, which was dependent on what branch you were on, and they'll give us the disjoint probabilities. So we can do that pretty quick, no big deal. Also notice that all four of those add up to 1. Explain how the stats indicate lung condition and smoking are not independent. Well, whether or not you smoke, it changes your conditional probability of developing the condition from 13% to 57%. So about four times the likelihood of developing this condition, whatever it is. I'm not sure. Might be emphysema or something like that. All right, so 13, that's not the same. So because the two conditional rates were not the same, then that means that they're not independent. But the way that we want to say it on the AP test is we want to compare the overall marginal distribution. So what percent overall had the condition? That would be 13% and 10%, which would be 23, to one of the conditionals, whether it's 57 or the 13. And I did it with those that smoked. And because those are not equal, they're not independent. So different ways, but the best way to do it is compare a marginal to a conditional like we've been doing all year. What's the probability that a randomly selected 6-year-old has this lung condition? So the overall, we said, was 23%. So 13 plus the 10% there would give you the overall. What's the probability that someone with the lung condition was a smoker? So we said that overall 23% had the condition, and of those that smoked and had the condition was made up 13% of all the people. So 13% out of 23% would give us a 56.5% chance that if it was a person who had the lung condition that they were a smoker. Fill in the Venn diagram with the disjoint probabilities. Well, all 4 of these disjoint probabilities will go in here. So smokers but did not have the condition would be 1%, 13% would be both. Had the condition as a non-smoker would be 10%, and then the rest are the 67% that were non-smokers without the condition, which was the majority of everyone. All right, that's it. So let me know if you have any questions. We will be doing a practice quiz the next day, so tomorrow, whatever that is for you. And then whenever you come back in person, the first day back in person, we'll take the quiz. So make sure that you're ready and you've got all of your homework caught up, and I'll see you guys later. Have a good one.